Hello everyone, in this video I'll be talking about solving partial differential equations using numerical methods. This is section 8.1 from chapter 8 on page 161. So we're going to begin with quick definitions of different partial differential equations. When we talk about PDEs or partial differential equations, we should note that we have at least two variables. One could be time, the other could be position, like x. One could be time, the other could be position, like y. Or could be two different position variables, like x and y. So all of these are within the category of PDEs. So for instance, in a PDE where I have time and position, like U could be concentration or temperature, T could be time, and X is the position. This is one of the types of PDEs that we're going to look at. It's one-dimensional on a steady state. We can look at elliptic. So this is called parabolic. We can have elliptic, but there's no time involved. We have positional dependence on x and y. Okay, so this is something like two-dimensional steady state problem. Okay, and then the last problem we can look at is hyperbolic equations, where we have second order in time and second order in position. Okay, and all of these, as I mentioned before, belong to the class of partial differential equations. Before we were looking at ODE, where we have only one variable, like either time or x or y, but here we have at least two. Okay, time and x, or time and y, or x and y, right? All right, so let's jump into the first example we're going to look at. So we're going to first start with parabolic PDE. Look at this diffusion equation. This is unsteady diffusion equation. We have time derivative, first order in time on the left, and second order in space on the right. So this is completely different from what we've done before, because before we had only one variable, now we have two. And because of that, we need to have two indices if you want to really convert them into like forward or backward Euler with the technique that we learned from chapter 6 and 5. We need to have two indices, because one is for time and the other one is for x. Okay, all right. So the problem that we have up here, okay, so that can be converted into a simpler form if you just absorb this alpha to t and then have a different variable like theta, right, which is equal to a times t. Then the equation we get actually is du d theta here, and alpha goes away because alpha gets absorbed into t. You can think of multiplying or dividing both sides by alpha, and then assume t times alpha is theta. Okay, so then you get this equation, but there's no constant anymore. And now assume we have three boundary conditions, one for time, two for x, because we have second derivative in x and first derivative in t, or time. Okay, so the boundary conditions are here. So the first corresponds to the x, and the second corresponds to time. So this is at x equals 0 and all time, u, or temperature, is 0. Let's think about u as a temperature. The other boundary condition is a temperature at x equals 1 and all time is 1. And then the last one is temperature for every x at t0 is 1. Okay, so we're going to skip the exact solution. This is given just to compare our numerical solution and make sure how accurate we are doing the problem. So we're going to skip the exact solution for now. All right, so these are evaluation of the exact solution. We're going to skip that and directly jump to solving the system using finite difference. Okay, so the left side is first derivative. So what we do is we apply forward Euler. So here's forward Euler version of the left side. First index corresponds to x, and second index correspond to y. So I is the x index and j is the y index, or t index. Well, in this case, t index because we don't have y, so the second variable is going to be t. Okay, so this is forward Euler in time because we know that j has gone up by 1. The right side is central difference approximation of the positional derivative, or x derivative, right? So this is d squared u dx squared. If you rewrite this using central difference in x, you would get this, and you see that j index doesn't change, so j, because this is only derivative with respect to x. So we're going to do central difference on x. So that's why we have I minus 1 here, I here, and I plus 1 there. Okay? This one we do derivative in time. That's why the time index goes up. Like j goes up and I is fixed. All right. So now the question is, what is unknown? So unknown is always the highest index in time. So everything in position should be known as long as the time index is j or j minus 1 or whatever less than j. Everything bigger than j in time index is going to be unknown. So the only unknown here we have is j plus 1. So I'm going to keep it here and move all other ones to the right side. Okay? So by doing so, we get an equation like this, where we have j plus 1 on the left side, uij on the right side, and this piece is written right here exactly. Well, multiplied through by delta theta, which is sort of our delta t, where, again, theta was alpha times t. Okay. So now we have this equation, and this is really straightforward to do. We assume everything on the right side is known. So this is at time j, at time j, time j, at different positions, like I minus 1, I, and I plus 1. We assume that we know all of them. We know ij, which is the same as this guy. So everything is known on the right side. We can go and calculate j plus 1. So let's see how this is done in Spreadsheet. So this is basically example 8.1. It's a transient heat conduction in a rod. The example we're going to look at, which is basically this equation, is you can think of a rod. So we have a rod, and initially at time 0, so this is at time 0, initially everywhere in the rod the temperature is, let's say, 1. Okay? So initially temperature is everywhere equal 1. Then immediately, as time goes by, we're going to put the left end, which is at x equals 0, we're going to put the left end on ice. So that's why we get the temperature at x equals 0 at all time equals 0. So if the left end is on ice, temperature on that should be 0 at any time. And the other end, we're going to keep it like a temperature 1. Then the question is, what is the temperature distribution from 0 to 1? So I want to know the temperature distribution for every point, not just the end point or left point and right point. So that's how we want, or that is the problem we're going to look at. Okay, so it's heat conduction in a rod. Initially everywhere is hot, temperature is 1. Then at time, say as time goes by, we're going to put the left end on ice and the right point on a source of heat, which provides like temperature equal to 1, and then ask what is the temperature distribution from left end to the right end. Okay, so we're going to go and look at how we can use a spreadsheet to do this. All right, so I'm going to show you the spreadsheet. Here is a spreadsheet. I'm going to move it down below this. All right, so a lot of colors here. Let me just go one by one. So this column is theta, so remember, theta is non-dimensionalized time, or alpha times t. So whenever you're talking about theta, you should think about time. This is time column, and you see that it goes down. Well, the number goes up, but as we go down along the column. So time is 0 here, 0.001, 0.002, you can think of seconds, like this is 0.003, 0.004 seconds, and so forth. So for every row, we have the temperature distribution in the rod from 0, this is the x value as I have here, this is x value from 0 to 1, with a separation of 0.01. For instance, if I look at this row, you should interpret these numbers as, okay, this is the temperature at this time point, 0.007, at this position. Along the same row, this cell refers to the temperature at this point, which is 0.1, at this time, which is 0.07. Or another example like this guy is the temperature at this position, 0.05, which is the middle of the rod, and same time point. So I read out time points on the left column, you read out the position from the top row. Okay, so with that in mind, let's apply our boundary conditions. Remember, the boundary conditions we have right here. We can look at this. So this says the boundary condition for x equals 0 for all time, temperature is 0. So here's x0, and as I go down along this column, which means x0 all time, right? Because that's the time vector or time column. So that means the first column should be everywhere 0, because this says so, right? It says x equals 0 for all time. So here's x0. This column is x0, right? Because that's x0. All time means all row. Okay, the next one is x equals 1 and all time. So here's x equals 1 and all time, which means this column. So I put 1 everywhere. Okay, as this one indicates. Now this guy is what this guy says at time 0 all x. So this row corresponds to time 0 all x, and I have to put 1. So I put 1 everywhere except the first one, because this conflicts. If I put 1 here, this is going to conflict with the first condition where I had 0 at position 0 and all time I get 0. So I keep the blue one as before. I just put 1 for the last boundary conditions from the second column all the way to the column next to the last one. Okay, so this piece is the third boundary condition. This column is the second boundary condition, and this column, this column is the first boundary condition. All right, so now we're going to look at how we can do the rest of it. So let's go down to discretization here. So all you need to do is just one cell. Okay, let's look at this cell. Well, this cell I'm not going to do because that has a boundary condition. So these two, we don't write any equation for these two columns because we already have the numbers. So we're going to start with this corner, okay, which is the second row, second column. Well, second column in x and second row in time. Okay, for this cell, we have exactly this equation. So this is the previous temperature, right here, the blue cell, plus this guy, delta T over del x squared, which I lump them into this cell, which is delta theta over del x squared, so that's the green cell, times uj minus 1, which means the purple cell, means previous row, right? We're looking at row j plus 1. So I have to go to row j, which is previous row, and column I minus 1, previous column. Okay, that's 1 here. And then minus 2 times the current column, previous row. So here is blue cell, current column, previous row. And then here is the next column, previous row. So here's next column, previous row. That's the brownish or whatever. Okay, that's it. So we have this cell. Oops. You're going to hit enter. Just scroll it down all the way to here. And then go all the way down. So there you go. You got a solution. Okay? And I can actually do this all the way down. So let's double click on that. All right, there you go. So some people ask about the color coding. For color coding, you can do that very easily. You just click on any cell you want to color code, and then you go to format on the top. You go to conditional formatting, and then here we're going to do add, and okay,